Hi everyone, welcome to the video on section 9.3, arcs and central angles. So I have a few things to define for you. First, I'm going to define the central angle. Okay, a central angle is an angle in a circle with its vertex at the center of the circle. So you can see, for example, I've got angle COW highlighted here, and I've defined it as 50 degrees, say. There's going to be another part of a circle that we will talk about in this section, and it's called an arc. An arc is an unbroken part of a circle. It's just a piece of the edge. Think about it as a portion of the circumference of a circle. And if you recall, circumference is the special word we use to talk about the perimeter of a circle, the distance around the circle. Okay, an arc is only a part of a circle. It needs two endpoints to define it. So the arc that I have highlighted in blue is arc CW. I'm going to name it with this symbol over the two endpoints, a curved symbol that resembles an arc. Now that's not the only arc I see. I also see arc CR, perhaps. Okay. And just like a segment, it's not going to matter what order you name the endpoints in. I could call it arc CR or arc RC, wouldn't really matter. How are we going to talk about how big an arc is? Well, there's actually a couple of different ways, a couple of different units. But for right now, we're going to talk about arc in kind of a surprising way. We're going to talk about it in terms of degrees. So how wide is the central angle that the arc sort of cuts off? So we're going to talk about arc CW, the measure of arc CW being 50 degrees. Now, there is another way to talk about it. We can talk about it in units of length, perhaps. How many centimeters in it? How many inches are in it? And that may have more meaning in certain situations. But using degrees can have some advantages as well. So I'll try and compare and contrast that for you throughout the chapter. So CW is 50 degrees. Let's see. What if I wanted to talk about arc CR, which I'll highlight in green? What do I want to talk about the measure of arc CR? Well, that's going to be 180 minus 50, because you can see that WOR forms a straight line. So straight lines form straight angles, 180 degrees in there. So 180 minus 50 will give me 130, so 130 degrees. Okay. So we're going to operate again in this chapter with the idea that the measure of an arc is the measure of its central angle. Okay. Now, arcs are like segments and angles. There can be congruent arcs. We're going to classify arcs based on their size. So here's a little bit more information on that. Congruent arcs, as you can imagine, are arcs either in the same circle or in congruent circles that have equal measures. Okay. Now that's important. They have to be in congruent circles. Well, why is that? Well, imagine another circle, okay, with a central angle of 50 degrees. Okay. Now, would you say that this arc with a measure of 50 degrees is congruent to CW? Well, they don't look the same size. Okay, so they're going to have to either be in the same circle or congruent circles. Okay. There are three major types of arcs that we'll talk about. Okay, the two arcs that I've mentioned so far have been minor arcs. Minor arcs. They have a measure of less than 180 degrees. Okay. So let's write down a few examples. So that would be CW and CR. Okay. Semicircles, as you can imagine, have measures of exactly 180 degrees. They are named using its two endpoints and then one additional point on the arc itself. Now, why do you need another point? Well, if I just talk about RW from the diagram above, am I talking about the top half or am I talking about the bottom half? You just don't know. So you do need a third point to indicate which piece of the circle that you're speaking of. So why don't I put point J down here, and then I'll refer to this as RJW. And now you can tell that I was talking about the bottom of the circle. If I'd wanted to speak about the top of the circle, I could have called it WCR, perhaps. Okay. And then major arcs have measures of more than 180 degrees. So they encompass, say, an obtuse central angle. So let's see. We could talk about, for example, let's put, I'm going to move a point J just a little bit, okay? And let's talk about JRC, arc JRC. You can see that that would be an obtuse central angle, so then that arc has a measure of more than 180 degrees, and therefore I need to name it using 3 endpoints. If I just call it JC, I would maybe think that I was talking about this purple arc. Okay, since I put the R in the middle, I know that I should go counterclockwise from point J all the way around to point C. Alright, so I've got some examples here for you. So I'm going to ask you to pause the video and try and put in some of these answers, and we'll go over them in the beginning of class tomorrow. And I'll proceed, presuming that you have tried 1 through 6. Right now you should have tried 1 through 6. If you haven't done so, again, pause the video, try 1 through 6. We'll go over some answers tomorrow. All right. So we're going to move on to the arc addition postulate. Now that term should sound somewhat familiar because we've had a segment addition postulate, we had an angle addition postulate, so now we have an arc addition postulate. The measure of the arc formed by two adjacent arcs, adjacent meaning next to one another, is the sum of the measures of these two arcs. No surprise there. So let's use the idea of the arc addition postulate to figure out this missing information. Now, I'm told that this central angle here is 30 degrees. Now what we figured out is that if the central angle is 30 degrees, then the arc that encloses it is also 30 degrees. And if you look down here at arc IK, we've been given the measure of arc IK, and so we can write in 50 degrees for central angle IRK. Okay. And then you can see that arc SIK, okay, is a semicircle, and we know semicircles have 180 degrees. So let's see, 50 degrees and 30 degrees plus a mystery measurement, okay, should be 180 degrees. And of course 50 and 30 is 80 degrees. So essentially if I subtract out the 80, how much do I have left for the measurement of x? 100 degrees. And that can be written both inside as a central angle measurement and outside as an arc measurement. Been asked for the arc measurement here, so I'll write in 100 degrees. Now IRK I actually had to figure out as I was figuring out the 100 degrees, so I can write 50 degrees in. Now remember, that was an angle measurement. I've been asked for an angle measurement, but of course we learned above that the central angle and the arc measurement are equivalent. And then finally we're asked for KEN. KEN. I'm going to highlight that in purple. KE and then all the way to N. Okay. So basically what we're seeing is that that is really the measure of, oh, sorry about that. Unhighlight that. The measure of arc KES. Oops, I'm writing it as an angle. Measure of arc KES plus the measure of arc NS should be equal to KEN. We can see that KES is a semicircle, And we know semicircles have 180 degrees. We know that arc NS is 30 degrees, so when you add 180 to 30 degrees, you get 210 degrees. I'm going to work out this next problem with you guys. Given the diagram below and given that arc BI is 40 degrees, which means the central angle is 40 degrees, find the following information. So number one, I was supposed to find the measure of angle BTI. Well, we've learned that if the arc measurement is 40 degrees, then the central angle measurement is also 40 degrees. Next, we're supposed to find the measure of angle BTE. So that's a central angle. Let's undo that. I was looking for a highlighter. BTE. Okay. So hopefully you can see that that forms a straight angle with our angle BTI. So we simply have to do 180 minus the 40 degrees to get 140 degrees for that large central angle. All right, next, what kind of triangle is triangle BET? Well, you can see that there's a large obtuse angle, 140 degrees. So it's obtuse. Okay. But even more than that, we've got something else going on. Okay. Look at BT, look at ET. Okay. Number one, they share an endpoint, okay, which on its own doesn't necessarily mean anything, but that endpoint is the center of a circle. B and E are points on the circle. What do you call a segment that connects the center of a circle to the endpoint on a circle? Well, we call that a radius. Okay, what do we know about radii? Well, we know that radii are all congruent. We know all the points on the circle are the same distance from the center. So here's what I can write. I can put that BT and ET are congruent. Triangles that have two congruent sides are also called isosceles. So it's both obtuse and isosceles. Okay. With that in mind, we can figure out what TEB is, what this base angle is. Remember by isosceles triangle theorem that if two sides of a triangle are congruent, then the two base angles are congruent. Now 140 degrees of my triangle is already taken up. So how much do I have left? I've got 40 degrees, but that's going to split evenly between my two base angles. So there we go, 20 degrees. Okay. I'm going to leave these two examples for class time. Okay. And then finally, I'm going to go over this proof with you. All right, so I've skipped ahead and written down the given information to get that out of the way. We've got a diagram where WZ is a diameter of circle O, and that OX is parallel to ZY. OX is parallel to ZY. Okay. We're supposed to prove that arc WX is congruent to arc XY. Okay, so that those two are congruent. Now, how are we going to prove that arcs are congruent? Well, we're going to try and prove that their central angles are congruent. So what we'd really like to say is angle WOX congruent to angle XOY? Okay, if we can prove that, then we can prove that the arc measurements are congruent. So let's see. We'll start with the idea that we've got many radii going on here, but let's look at this triangle here, OZY. Let me highlight that for you, OZY. Okay. If you notice, it's formed by two radii. Two of the sides of the triangle are radii. So, of course, radii are congruent. Okay. So I can use that as a reason. By definition, radii are congruent. So now, I mentioned that it was an isosceles triangle. What do we know about isosceles triangles? Well, that their base angles are congruent. So you might be able to see where I'm going with this now. I can say that angle OZY is congruent to angle OYZ by isosceles triangle theorem. Okay. Now, what can I do with that? Well, remember, I have parallel lines here. Okay, so for instance, I see OZY corresponding to one of the central angles that I'd really like to prove congruent. So let's say that angle OZY is congruent to angle WOX, because if parallel lines, then corresponding angles are congruent. And then additionally, I see that the other base angle from the blue isosceles triangle, what was that? Angle OYZ. Okay. Angle OYZ, so here, emphasizing that highlight right now, should be congruent to XOY. XOY. Take a look at those two angles. Okay. They're actually alternate interior. Okay. So that was, let's see, XOY, angle XOY. If parallel lines, then alternate interior angles are congruent. Okay. So let's cut out the base angles and focus on these angles up here that I wanted to prove congruent in the first place. Angle WOX is congruent to angle XOY, and we can say that that's true via either transitive or substitution. I know most of you prefer substitution. Okay. And then finally, I can say with our new rule from today that arc WX is congruent to arc XY, and that's because the measure of an arc is equal to the measure of a central angle. Okay. So we're not going to do a ton of proof in this chapter, but here and there we'll test it out using some of the new theorems, as well as some oldies but goodies like isosceles triangle theorem and our parallel line theorems. All right, I'll see you in class tomorrow.